Welcome to the video on epoxides. Epoxides are three-membered rings that contain an oxygen, like we see here. We create epoxides using an alkene, reacting it with a peroxy acid, which I'll talk about in just a second, to get that three-membered ring with the oxygen. Very often, epoxides are not final products, but they're more intermediate. And so we'll talk about that a little bit too. A peroxy acid is a reactive species that adds an oxygen across a double bond. And so if we look at this compound right here, here is a typical peroxy acid with what looks like a carboxylic acid here with this additional OH. So this bond right here between the oxygen and the oxygen is the very reactive bond in this molecule. And it turns out this oxygen right here is the one that gets inserted in the epoxide. One very common example of a peroxy acid that we will see is MCPBA, which is metachloroperoxybenzoic acid, and that's shown here. Again, here's that very reactive bond. Also, peracetic acid. The mechanism to create the epoxide from the alkene is a little bit crazy. We'll follow all these arrows, but basically it's a concerted mechanism. All these pink arrows shown over here happen in the same step. So we have this transition state here that has the epoxide partially formed in that transition state. And then finally, here is our epoxide in the final product. So we have peroxy acid reacting with an alkene, and it gives us a carboxylic acid and an epoxide. Now, if we look at the stereochemistry that happens in an epoxide, if your alkene is trans, shown here, then we end up getting an epoxide where the groups are trans as well. So if we have an alkene where the big groups are on the opposite side of the double bond, we end up with an epoxide where the big groups are now one goes back, one comes forward. If, however, our alkene is cis, shown down here, where our two big groups are on the same side, then our epoxide is also going to have those two big groups on the same side. So if your alkene is more electron rich, then our reaction actually happens faster. I told you that epoxides are often intermediates. So we form the epoxide, but then we very quickly react it. It's a pretty reactive species. It's pretty unstable. So if we talk about the reactions that epoxides undergo in acid, first, we protonate that oxygen. So we have a proton transfer here where we end up with the positively charged oxygen over here. So the way that that proton transfer happens is the lone pair from the oxygen reaches out and forms a bond with the acidic proton. And then the two electrons here get kicked back on, so we form water. So we have this positively charged oxygen shown here. And then what happens is because this positively charged oxygen is right here, it makes this carbon down here even more reactive because these two electrons would prefer to be on the oxygen. And so what happens in that second step is we take the lone pairs from the oxygen of the water, and that forms a new sigma bond with this carbon. That first arrow is nucleophilic attack, and then that carbon in turn breaks this bond right here. So the two electrons in this bond right here, in that very highly reactive, strained three-membered ring, these two electrons bust open the ring, and those hop onto the oxygen shown here. This second arrow indicates loss of a leaving group. And because the group that is attacking is neutral, we noticed that down here it's positively charged. This group that leaves right here is neutral. So this OH becomes this OH right here, and this H2O that did the attacking is now up here. Now in the last step, to get to our final product, we have another molecule of water that's going to deprotonate that charged oxygen. So we're going to pull that proton off. These two electrons will kick back onto the oxygen. And so we end up with a diol. A diol is a compound that has two alcohols. So we end up with this diol. It's a 1,2 diol, and it turns out that it's a trans 1,2 diol that we form when we have an epoxide and we react it with water. This is an example of acid-catalyzed epoxide ring opening. So in contrast to the acid-catalyzed epoxide ring opening, this mechanism is the base-catalyzed. And so the first step in the base-catalyzed is we have this strong base that is going to now attack the carbon that is in the epoxide, and then that is going to force this bond here, these two electrons, to kick up onto the oxygen, opening up that ring. And in the last step, we have proton transfer. So the negatively charged oxygen gets protonated from this proton in the conjugate acid of our base. And so we have proton transfer, and then we end up with our product. Here, this first arrow is nucleophilic attack, and the second arrow is loss of a leaving group. And then the third is proton transfer. So if I compare and contrast real quick and look at the acid catalyzed, we have a proton transfer. Then we have attack of the nucleophile, loss of a leaving group here. Then we have an additional proton transfer. For the acid catalyzed, there's one additional step, which is the original proton transfer, which activates this O to become a leaving group. And in the base catalyzed mechanism, we only have attack of the nucleophile, which is charged, so we don't have to deprotonate. So attack of the nucleophile, and then loss of a leaving group, and then that leaving group needs to get protonated at the end. And so there's the difference there. If we're looking at the base catalyzed mechanism specifically, and we're looking at an epoxide that is not symmetrical, for example, one of the carbons has only 2 H's on it, and the other carbon has at least 1 carbon on it, then this situation where we have the nucleophile attacking the epoxide to open the ring is going to be very similar to an SN2 type reaction. So that strong nucleophile, charged nucleophile, is going to attack the carbon that is less hindered. And so in a base catalyzed situation, the nucleophile attacks the carbon of the epoxide that has the most room, that is the most open, and that is the least hindered. And so then we end up with our product where the alcohol, right, we still have to protonate that oxygen to get the alcohol. The OH group ends up being on the carbon that is more hindered, and your nucleophile is on the carbon that is least hindered. However, in contrast, when we have an acid catalyzed epoxide ring opening, we protonate first using that acid, and what happens is the nucleophile ends up attaching to the carbon that is more hindered. And the reason that that happens is that this is more SN1 like. So it could be that this bond shown right here in the reaction is actually partially broken already, so that this carbon right here is actually partial positive, or potentially we could even think about it as a carbocation. So in epoxide ring opening, we don't have complete loss of a leaving group first, but we have a little bit of a loss of that leaving group. So it partially breaks, as shown right here. Acid catalyzed, the nucleophile attaches to the carbon that has more substituents, so that we can think of that as an SN1 situation. We can think of that as a carbocation situation. And base catalyzed epoxide ring opening, that nucleophile, that strong nucleophile, acts more like an SN2 reaction, where we go to the carbon that has more room and we get that backside attack. So I think this is a nice review, thinking that we just finished the substitution chapter, that we have an example of an SN2 here with the base catalyzed epoxide ring opening, and we have an example of an SN1 with the acid catalyzed epoxide ring opening. Okay, good luck.